A 12,000 liter tank of water is filled to capacity. At time t equals 0, water begins to drain out of the tank at a rate modeled by R of t, measured in liters per hour, where R is given by the piecewise defined function. So here's the piece from 0 to 5, and here's the piece for t greater than 5. A, is R continuous at t equals 5, and show the work that leads to your answer. Well, if you plug 5 in for the top one, and for the top function, you get 375. When you plug 5 in for the bottom, you get 367.879. So I don't think I ever answered, is R continuous? R is not continuous. So you continuous. Letter B, find the average rate at which the water is draining from the tank between time t equals 0 and time t equals 8. Well, this is the function. This is rate. So if we're going to find the average value of the function, now we use the actual function. So from 0 to 5, remember for average value of a function is 1 over b minus a, integral from a to b of the function. So now we have 1/5, and we're going from 0 to 5, because b minus a is 5. So we have this piece from 0 to 5, and then we have to switch over to 5 to 8. And 8 minus 5 is 3. So we have the other function. So when you do all of this on the calculator, you get 258.052. Letter C, find R prime of 3 using correct units. Explain the meaning of the value in the context of this problem. So 3 is between 0 and 5, so we're going to take the derivative of that function right there. Now, I did the derivative by hand, but that's really not necessary because math number 8 will do derivative for you. So all I needed to really do is write R prime of 3 is equal to 50 and use the calculator to get that answer. Now, that's liters per hour squared. And the meaning of that is the rate at which the water is draining at t equals 3. It's important to say at this time we get this value. Well, the rate is increasing at 50 liters per hour squared. Right, but do not solve an equation involving an integral to find the time a when the amount of water in the tank is 9,000 liters. So we start with 12,000, that's given, a 12,000 liter tank. And we're going to minus out the displacement, and we want to know when will that end up being 9,000. So that's the unknown right there. Here is the rubric. There's A, there's B, there's C, and there's D, and you can see the points off to the right there. This is a calculator problem. A storm washed away sand from a beach, causing the edge of the water to get closer to a nearby road. The rate at which the distance between the road and the edge of the water was changing during the storm is modeled by, so f of t is the change. So it's like they're giving you the derivative, but they're not telling you it's a derivative. They're saying the function is actually the rate, meters per hour. T hours after the storm began. The edge of the water was 35 meters from the road, so there's your initial value, when the storm began, and the storm lasted 5 hours. So we'll keep that in mind. Storm lasted 5 hours. The derivative of f, and they just flat out give this to you so that you can plug it in the calculator. What was the distance between the road and the edge of the water at the end of the storm? So it starts out with 35, and then you add the integral from 0 to 5 of f of t dt. That ends up being 26.494. Using correct units, interpret the value of f prime of 4 equals 1.007 in terms of the distance between the road and the edge of the water. So this is the rate. The derivative will be the change in the rate. So after 4 hours, the rate of change of the distance between the road and the edge of the water is increasing at a rate of 1.007 meters per hour squared. So if they give you f as a rate, then the derivative is the change in the rate. At what time during the 5 hours of the storm was the distance between the road and the edge of the water decreasing most rapidly, and justify your answer? So we want to know where the first derivative is equal to 0. Now I used my calculator to do this, and it turns out it's at 0.66187 and 2.84038. So here are the endpoints, f of 0 and f of 5, and here are the critical points where we could have either a local minimum or a local maximum. So the distance between the road and the edge of the water was decreasing most rapidly at time t equals 2.840, because we can see this is the biggest negative number for the rate, and that's hours after the storm began. After the storm, a machine pumped sand back into the beach so that the distance between the road and the edge of the water was growing at a rate of g of p meters. So we're putting sand back on the beach, where p is the number of days since pumping. Are we putting sand back on? Yeah, putting sand back on. Write an equation involving an integral expression whose solution would give the number of days that sand must be pumped to restore the original distance between the road and the edge of the water. So this right here is the displacement. This is how much was taken off. Well, we want to reverse that. We want the negative of that. And if this is pumping sand back on, then that has to go from 0 to whatever time it's going to take. We don't know what that time is. That's what we're trying to find out in letter D, or that's what we're trying to represent. Here's the rubric and the points that go along with each. There we go. That kind of snapped back up. There we go. For each problem, find the values of C that satisfy the mean value theorem. Well, the mean value theorem says that we have a C value, we have somewhere where the instantaneous velocity is equal to f of b minus f of a over b minus a. Somewhere the instantaneous velocity is going to be equal to the average velocity. So in other words, y prime of c is equal to y of 6 minus y of 3 over 6 minus 3. We take the derivative here, which is negative 2c plus 8. And when we plug 6 in, we get negative 5. 3 in, we get negative 22. So that ends up being negative 9. So if we subtract 8, we get negative 17. So at negative 17 halves, the instantaneous velocity will equal the average velocity. And that's your mean value theorem. Here's some more implicit differentiation. We take the derivative of 1, that is 0. Derivative of 3x is 3, so we have first times derivative of the second, first, derivative of second, plus the second times the derivative of the first. So anything that doesn't have a dy dx, we get to the other side, there's negative 3, and minus 4xy squared, that's right there. And then we divide by 4x squared y, and you end up with the answer right there. Find the values on which the function is increasing and decreasing. Derivative set equals 0. X equals 3 is a critical value. And then we plug in 2 into the derivative. Negative 4 plus 6 is positive. Plug in 4, negative 8 plus 6 is negative. Well, this is an upside down parabola, so it's going to increase and then decrease, of course. So increases from 0 to 3 and decreases from 3 to infinity. 0 to 3? Nah, we want negative infinity to 3. My apologies. On this one, we're going to let u equal x over 7. If this was 16, it'd be x over 4. If it was 25, this would be x over 5. Because we're going to multiply by 7, take the derivative. There's the derivative. And now, instead of dx, we're going to have 7 du. So there's 7 du. And we're going to put 7u in for x squared, which makes 49u squared. So there's 49u squared plus 49. We're going to factor out the 49. 7 over 49 is 1/7. This is the derivative of inverse tangent. So we have inverse tangent of x over 7, and then, of course, plus c.